We discussed, at the end of yesterday, we discussed one-dimensional low concave distributions. And let me just remind you, so there was some proposition that basically they all bounded between some exponential and the constant function. So if you have, if x is isotropic means zero mean and variance 1, isotropic low concave random variable in R. So let me emphasize it's in R, and density is rho. Then the density is bounded for any x. The density is bounded between an exponential and let's put prime and some indicator function. Okay, and these are universal constant. One corollary was reverse Hilbert inequalities. And another one, okay. Now, I did not have time yesterday to discuss isoperimetry in the one-dimensional case. Everything is pretty much understood except for base constants. If you want up to a constant, everything is pretty much understood. And for example, we have the following proposition. So I will just state it now. Okay, so same assumptions. So, okay, x isotropic low concave in 1D. And as for isoperimetry, let's fix some number p. And let S be any subset, Borel measurable subset of measure p. Now, as in Joseph's lecture, I'm going to deal with isoperimetry through epsilon neighborhoods. So you write, okay, so then for any epsilon between 0 and 1, the claim is that if I look at the measure of the epsilon neighborhood of S minus itself, okay, so S epsilon, as yesterday, is the set of all points in R where the distance of the point from S is at most epsilon. So this is the epsilon neighborhood. So the claim is that the epsilon neighborhood is at least a universal constant times epsilon times the minimum of p and 1 minus p, where c is universal constant. Okay, so we have a completely uniform bound for the you know that if you take any subset, so suppose that P is 1/2, if P is 1/2, the set must have some area which is kind of close to the center of the distribution, and therefore its epsilon neighborhood you should get at least something, and you indeed get here there is epsilon, so you get something like epsilon. Okay, I will not. So the proof is not. The proof is. I think I outlined it in the lecture notes. So basically, there is a result of Bobkov which reduces matters to half line. So actually, there is a very nice argument based on no concavity. If it's a finite union of intervals, you can move them, and things just get better. And it's enough to look at half lines. And the second thing is that there is a reduction to the case of P equals 1/2. Thanks to the concavity of the isoperimetric profile. Now, yesterday in Joseph's lecture, this was a black box in high dimension, but in one dimension, just it's a simple thing to prove that there is this concavity of the profile. So you managed to prove in one dimension this isoperimetric inequality. In particular, for isotropic low concave measures in R, the Chigger constant that was defined in Joseph's lecture is bounded, and also the Poincaré constant. All of them have the order of magnitude of universal constants. They are bounded between two constants that are can be explicitly written. And the only, I mean, if you want best constant, it's not known, but if you want to know up to a constant, there's no question. Okay, so this was about yesterday. Any questions about yesterday and about the the little additions that I added today? Okay, so as we said, there are several methods and techniques to study high-dimensional distributions with convexity properties, and in some sense, this fits the playground for various techniques. Yesterday, we saw the heat semigroup approach in Joseph's lecture, and today, I'm going to discuss optimal transport with the Monge cost. Okay, which is a useful technique in this business. Now, I see in this audience, real experts on optimal transport, so if anyone wants to make a comment or say something, it will be most welcome during this lecture. Okay, what's optimal transport? So we have two measures on Rn. Absolutely continuous measures on Rn. And they should have the same total mass. So the measures are finite. Okay. No negative measures, and should have the same total mass. Okay, so for instance, maybe just to have a picture, maybe mu1 has this density, and maybe mu2 has another density. Okay, and the Monge problem is the following question. So we look on all ways to push forward one measure to the other. I'll explain in a second what the push forward is. And among all ways to transport mu1 to mu2, we look at the ones that we try to minimize the cost. Okay, so so that's the Monge problem. Too high. Okay. So there's the Monge problem. And so push forward, so this push forward, this means that, so if you take any, so if this is mu1 here and mu2 is here, and I take, I take any set here, and this is the corresponding, so this is A, and this is the, it's common to work with pre-images, it's better in measure theory. So this is the pre-image, so I want them to have the same mass. So it requires that S minus 1 of A is the same as mu2 of A for any Borel set, A. Okay, so what do we see in this Monge problem up in the skies here? We see that we look on all ways to rearrange the mass, okay, to find a way to map the measure mu1 to mu2. And for any such measure, we have a cost, okay? And the cost is the distance, the average distance the point travel. The point x travels to S of x. The cost is the distance. And we try to minimize the total cost, the integral of S of x minus x, the distance with respect to the measure mu1. Okay, so this is the Monge problem. It has some motivation from going back to the 18th century. And there is actually a nice heuristics about this problem. So before discussing why it is existence of minima, etc., let's discuss Monge heuristics, which goes back to 1781. And this is the following. So for the optimal T, suppose there is an optimal, there is an optimal map. There is an optimal, if you assume finite first moments, there is an optimal map. But for the optimal map T, the following holds. For any point x, so the line segments from x to t of x. So we look at all of these line segments from x to t of x, where x ranges over the support of mu1, I mean, wherever it is defined. If you look at all these line segments, they do not intersect unless they overlap. Okay, so that's the quite remarkable property of the Monge cost, of the optimal transport with the Monge cost. And the argument, or the reason for that is pretty simple. It is just a triangle inequality. Suppose you have a map which is optimal, so it transports mu1 to mu2 in the most efficient way. Okay, in the 18th century, maybe formal existence was not a big deal, as it is in the 20th century and 21st century. But we consider the optimal map, and suppose that it takes the point x to t of x. Right here. Suppose it takes x to t of x, and suppose it takes the point y to t of y, such that these segments intersect. We assume by contradiction there's an intersection. The claim is that this cannot be optimal. Why it cannot be optimal? Because if I, instead of connecting x to t of x, I connect x to t of y, and I connect y to t of x, okay? Then the sum of this plus this, so by the triangle inequality, x to t of y is smaller than this thing, y to t of x smaller than this thing, so together, this cost plus this cost is smaller than this plus this, just by the triangle inequality. Now, of course, how do you construct a better map given such a violation, such an intersection? So you take a small amount of epsilon mass here and here. No, sorry, take a small amount of mass here. Now, originally, x was mapped to t of x and y to t of y, so this little region here supposedly was mapped here, and this region was mapped here. Now, if you switch them, you would get a better map, which contradicts the optimality. And therefore, the optimal map should not contain segments that intersect. This was the heuristic by Monge. Okay? So this is his reasoning. And let's note that it only uses triangle inequality, nothing else. So it's not so much about the specific geometry of Rn, and that this principle, this should work in any metric space, basically. Any, let's say, geodesic metric space. I want to have geodesics. So Riemannian manifold, Finster manifold, whatever you want. Well, under some regularity assumption, you'd expect this principle to hold in great generality. And the conclusion of this heuristic is that the optimal T induces a partition, the optimal transport map T. So maybe there is a, okay. It's not unique, but any optimal map, transport map T, induces a partition into segment. So if I look on all points, if I look on xt of x, this is one segment, yt of y is another. They could overlap, okay, but they can never intersect. So I would get a disjoint family of some kind of maximal intervals that should form, well, maybe partition of some of the support of V of some domain in Rn. I'm not saying, say the support of mu1 or something. At least some domain in Rn should be partitioned into line segments. Okay, so that's what we hope to get from optimal transport map. Okay, so this is at least heuristically what you should get. These line segments, these are called either, you can call them transport rays. And I mean, recently, it's also common to call them needles, at least in the context of geometric inequalities. Sometimes we call them needles. And another thing is that while the optimal transport map is not going to be unique, somehow this partition is unique. So in some sense, it's the most fundamental object in this problem, this partition into line segments, and transport happens only along these line segments. Okay, so this is about the 18th century. So, by the way, if in English there is a nice review of Mond's work by Cayley from roughly 100 years later, which is pretty readable and is also a bit critical, but you can understand what Monge knew, and indeed he had this picture of this partition, or this transport lines, or this envelope, we call it. Okay, so this is 18th century. Now let's move forward in time to the 1930s, 1940s, to the work of Kantarovich and other people on linear programming, on duality in functional analysis, such things. Okay, so from now on, it's going to be more familiar rigorous mathematics. So linear programming relaxation. Okay, what's one of the features of a transport map is that you kind of have to assume that the measures are absolutely continuous or they have some regularity. You cannot just take two discrete measures and transport one to the other because you cannot split atoms. Okay, so an issue is that transport maps can't split atoms. Okay, so you cannot transport a measure of two atoms with weights half and half to a measure whose weights are 2/3 and 1/3. There's just no such map. Okay, so what we should do is that we'll consider, rather than consider transport map where each point is mapped to a single point, we're going to allow a relaxation where we can split the mass between several points. So it's not, a point is mapped to some distribution. That's the idea. So we consider a transport plan which is also called a coupling, like there were couplings yesterday in Joseph's lecture. So a coupling in place of a map. So what's a transport plan? Or what's a coupling? So a coupling of two measures, coupling of mu1 and mu2 on Rn is a measure gamma. All measures are, say, Borel measures. Gamma on the cross product, Rn cross Rn in other dimension, such that it's marginals. So if I look at, okay, such that for any set A, if I look at gamma of A times Rn, I get mu1 of A. And if I look at gamma of Rn times A, I get mu2 of A. Okay, so if these are two copies of Rn, then the first marginal is going to be mu1, and this marginal is going to be mu2. Maybe we can write it as pi1 of gamma is mu1 and pi2 is mu2, where these are just the projections of the first and second coordinates. So pi1 of xy is x, and pi2 of xy is y. Okay, now this is coupling. Already we see that given any two measures, mu1 and mu2 in Rn, there exists at least one coupling, which is just the product measure. If you have if you think about it in terms of random variables, this means that coupling means putting these two random variables on the same probability space. And if you take the product measure, it means that you've used them as independent random variables into distributions. Also, you should note that any transport map induces a transport plan. So if S pushes forward, if T pushes forward mu1 to mu2, then we can construct a coupling. How would you construct a coupling? Let's define S of x to be the pair x T of x, and then gamma, which is the push forward of mu1 under S. So this is a coupling. Let's see what it means in the picture. So if I look at this, the same picture, so if here lives mu1 and here lives mu2, and this is the graph of t. Okay, so this is x and this is t of x. Then whenever I take a subset here of measure A, okay, gamma is such that this is the same measure because this projection gives me A. But if I look at this projection, because of this property of the because T is a transport map, I'll get the measure of mu2 of this set. Okay, so therefore this is a coupling. And in fact, there are many, many, many couplings. The space of all couplings is a convex set. Okay, so an advantage. Space of couplings is a convex set. So if I take two couplings and take their average, this is again a coupling. Okay, so the space of transport maps is somewhat complicated, but the space of couplings is very simple. Okay, now what's the relaxed formulation of the Monge problem? So the LP linear programming formulation of Monge problem is what? So I'm going to take the infimum not over all maps, but over all couplings. So let's write it over all gamma, such that pi 1 of gamma is mu1, pi 2 is mu2. And what is the cost now? So earlier we just look at the distance that a point travels from x to t of x. Now the point x is mapped to some distribution of y's. So we're going to take the average distance the points travel, which means that we're going to take x, the distance between x to y. Okay, it's a more symmetric formulation. You don't transpose mu1 to mu2. It's 2 points x and y. And if a fraction of the points at x is mapped to y, then we pay the cost of transporting this mass at x with mass at y, which is the Euclidean distance. Okay, so this is a relaxed problem, and at least in principle, a priori, this is not larger than the Monge cost because one of the contestants in the infimum is the transport map. Okay, now the nice thing when you have a convex set on which you optimize a linear function in gamma is that you have a duality.
So this is a different problem than the original one? Because
Yeah.
It's not symmetric, right? So
Yes. So a priori it's different, but the theorem would say that they are the same.
And if you place like mu2 instead of mu1 there, it's also a different problem, or is it something like
A priori, there are all three different problems. You can have a map from mu1 to mu2, a map from mu2 to mu1, or a coupling. A posteriori, they are all the same problem. Okay, so Kantorovich duality. More questions? Hi, Matthew. Kantorovich duality. Okay, so assume that, so let mu1, mu2 be absolute continuous measures, finite measures. Same total mass. And we need some regularity, so I want to assume that this is finite. Okay? Now I bring back this board. Now let me denote. So when the two measures overlap, perhaps it does not make much sense to move the shared points, right? I mean, if somehow in the Monge problem, it's not true for L2, but for L1, if the measures overlap, then whatever is already, you can, I mean, you don't move things that you don't, unless you have to. So in this problem, it makes sense to denote the difference of these two measures, mu1 minus mu2. So this is no longer a positive measure. It could attain negative value, but that's OK. Then the claim is that the following things are equal. So first of all, I write minimum, not infimum, because it is attained. So the minimum over gamma of this cost over all couplings. It is the same as this. OK, let me write here the minimum over T that pushes forward, over SSF, pushes forward mu1 to mu2 of the transport cost. OK, this is maybe expected. In linear programming, the optimum is attained at a vertex. You would expect things like that. But what's not completely obvious is that there is a dual formulation. And the dual formulation apparently involves one Lipschitz functions. So if I take the supremum over all one Lipschitz functions of this integral, then I still get the same number. And in fact, not only the numbers are equal, there is also correspondence between the optimizers, gamma, mu, and S. OK, so just a few comments. So this thing, this is due to Evans and Gangbu in '98. And this is harder than this equality, and also will not need it. So I will not prove this equality here. Although, actually, later we discuss the structure of Lipschitz functions. From this structure, you could understand why. Yeah, you could understand why this is correct. But OK, at least we'll not prove it right now. Maybe in 20 minutes. Yes?
Small typo.
Typo. Well.
The last mu is mu1.
mu1, yes. Thank you, Joseph. Yes. OK, so let me prove this thing at least, in some detail at least. OK, so there is the easy direction where sup is smaller than inf. So you take gamma and u, take gamma, which is coupling, and u, which is one Lipschitz. U1 Lipschitz means that u of y minus u of x is at most x minus y. OK? So now you can, let's integrate this inequality with respect to gamma. So what do we get? OK, so integrate with respect to gamma. So we're going to get that the integral of x minus 1 d gamma is at least the integral of u of y minus u of x d gamma. Now, since gamma is a coupling, it means that integral with respect to y of a function is like the integral with respect to the push forward of gamma with respect to the second coordinate, which is mu2. So the first thing would give me the integral of u with respect to mu2. And the second would give me the integral with respect to mu1, which is the integral of u with respect to d mu. OK, so we see that for any gamma and for any mu, this thing is larger than this thing. So the infimum over the cost is at least the supremum of the Lipschitz functions. That's the easy direction of the supremum and the infimum. And OK, so we kind of see from this argument that maybe a dual object to the transport plan, to the gamma, is indeed this one Lipschitz function u. So this gives each one Lipschitz function gives me a lower bound for the transpose cost, and each coupling gives me an upper bound for the transpose cost. OK. And how did it form? Oh, well, OK, maybe this is, I don't know. Yeah, you're right. One of them should be fixed. Yes. You prefer this way? OK. 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 No, this is the minimal change, I think, to put it this way. Let me put it this way. Yeah. Good. So everybody's alert. So 1 point to Joseph, 1 point to Cyril. Very good. Okay. Now about the difficult. So now about the equality. So for the equality, we need to find gamma and u such that equality is attained. So if equality is attained, it means that this is the maximum, this is the minimum, this is the maximum, and you have equality. Okay, so what the inequality that we used was this thing here. So what we need that to know that for any 2 points, x and y, in the support of gamma, uy minus u of x equals the distance. Okay, that's our goal, to find such a coupling. Okay, so now this would be our goal. Now there are a few steps. First of all, we look at this relaxed linear programming problem, infimum over gamma. So the claim is that the infimum is attained. The infimum over gamma of the cost is attained by a simple compactness argument. What's the compactness argument? So let's do the following thing. So let's do the compactness argument as follows. I'll do it in, I can take the 1 point compactification of Rn and look at the space of all couplings on this compact space, and this space of couplings is a closed set and convex set. And by Lauglo's theorem, it's compact in W star. And the integral, so integral with respect to bounded functions would be continuous, but this integral would be lower semi-continuous. So this is lower semi-continuous because it's the supremum of integrals with respect to bounded functions. And supremum of continuous functions is lower semi-continuous. So the infimum is attained. Lower semi-continuous on a compact set attains its minimum. Okay, so the optimum of gamma, I claim it is attained. Once you know it's attained, let's understand the optimality of gamma. So what's the optimality conditions for the minimizer? So this is pretty much like this Monge heuristic a bit. So the claim is that if we take any pairs of points in the support of gamma, and any permutation, sigma, pi is, no, actually, pi was, let me take sigma. Any permutation, the claim is the following thing, that if I look at the cost of transporting xi to yi, okay, so this would be at most the cost of transporting xi to some permuted manner. Okay, so if I have this, I know that x1 goes to y1, x2 goes to y2, etc. If this inequality was violated, then I could make some switch and take some epsilon mass here, and switch it and improve upon this optimal map. So it means that there cannot be a permutation that improves for me the cost, and therefore this would be this is the optimality of gamma. Okay, and now, yes, please. Yes, I claim this is compact in weak star topology. So there are a few ways to do it. Let's suppose that I had 1 point at infinity, and I look at the 1 point quantification of Rn. So the measure does not charge this extra point at infinity. Okay. So I look at the space of all measures whose margin on the first coordinate is mu1 and the others is mu2. They claim this is a closed convex set in the space of measures on Sn times Sn on the compactification of and any closed convex bounded set is probability measures, finite measures. Yeah. Okay. Okay. Yeah. Okay. Now the claim is, okay, very good to have these optimality conditions. And now, now we argue, now we want to find the function u. And this is a variant of Rockefeller's theorem in convex analysis. So now the claim is that, so now we need to construct u. How to construct u? So the idea is okay, the claim is that, so I claim that given these optimality conditions, there exist u from Rn to R, one Lipschitz, such that this, what I said is holds, such that u of y minus u of x equals x minus y for any point in the support. How would I construct such a map? So the idea is let's fix some point in the support, x0, y0 in the support. And our idea is going to be as follows. We're going to stipulate that u of x0 is 0, because u is up to a constant. I mean, you don't care about adding a constant to u changes nothing, because mu has total mass 0. So let's assume that u of x0 equals 0. Again? Val uy more u of x, yeah, uy of ux is the distance between x and y. So it was. You want y minus x here? No, what? I mean,
was worried that if you swap x and y, then you have a contradiction that you can't swap because support is not symmetric.
Support is not symmetric, of course. Yes, yes. Always ask Joseph, okay? In case of a doubt. Very good. Yes, it's not symmetric. Right, it's important. There is a direction. It's a good point. The transport is you transport in the ellipse is going to increase along the transport, actually. So there is a direction, uy minus ux, but not the other way around. Okay, so the idea for constructing u is the following. So we're going to take, let me write the formula and then we'll discuss it. The formula is the following. So I'm going to take the supremum over all lower bounds. So I take any n tuples of points in the support. In the support of gamma. And then I try to do the following. I claim that any expression that I'm going to write here is going to be a lower bound for any Lipschitz function map u with ux is 0 equals 0. So I claim that if I look at, let me just draw it for myself. So I look at these points, xn to yn, and then at the end, the point x. So I claim that if I look at these points, and let me put in some green, this thing here. Okay, so the claim is that I'm going to get, how do I get bounds for u? So if I go, u of x is 0 equals 0. If I go to y0, then I know that the function should go up. It will be y0 minus x0. Now, what's the lower bound when I go here? If it's function, it cannot go more than the distance between y1, y0, and x1. And then plus y1 to x1, so from x1 to y1, and then minus from y1 to x2, etc., until the last thing I get from, this will be with a plus, because I know by my assumption that going from x to y should increase the value by xn minus yn. And when I go back to x, I have to decrease it. Okay, so the claim is that each of these things, this is a necessary lower bound for u. Okay? And I take the supremum of all these lower bounds, and I claim that this works. Okay? So let's see. Why does it work? So why is it 1 Lipschitz? First question. OK, let's say why u of x0 is actually 0 here. With this definition, it's not completely obvious that u of x0 is going to 0. And the thing is that if I put here x0, what would I get? So if x0, if the green line goes back to x0, I'm going to get some permutation of the points. It means that I have a permutation which is just cyclic shift by 1. And the thing with the plus is the left-hand side of the optimality condition. And the thing with the minus is the right-hand side for the map sigma, which is cyclic shift by 1. And therefore, the plus loses the fight against the minus, so to be non-positive, what's written here. So the superpoint will also be non-positive, OK? But I can choose something trivial, like if I choose x1, so if I choose for just 1 point, n equals 0 something, then I get that it's, I get y0 minus 0 minus this thing, so I get that it equals 0, just because if I take 1 point. So this was the only place where I used the optimality condition, u0 equals 0. OK, very good. Why is u1 Lipschitz? Because it's the supremum of many functions. Each of these things, so if I fix this family of points, this is a 1 Lipschitz function in x. Right? So it's minus some distance function, it's 1 Lipschitz. Supremum of 1 Lipschitz function is 1 Lipschitz, so it's 1 Lipschitz. And how do I know why this condition? Let's call it star. Why star holds? Well, because if you have some, if I know that, OK, let's now put x to be here. So if I know that some point is in the support, suppose that you reach here some value. So this is, suppose this is x. OK, and you know that y is also in the support. So you could, look, I mean, just from this picture. So whatever you get from, suppose you get some value for y, OK? Then the values that you get for x would be, if I add this extra point x, yeah, right, wait. If I, OK, suppose I get some value for x with some chain. No, I do it the following way. OK, I look at the chain. OK, so whenever I have any, I look at the chain that gives me, that goes for y, OK? So the chain for y, I can make it sort of end with this segment plus some little, any chain for y, I can make it end with this segment, basically, because xy is inside. So any chain that will end at x, I could add to it this extra edge that ends with y, or something very close to y, and get an extra distance. So the distance, the value of u at this point must be at least as large as the value of u at this point, right? Because I add this edge, and for which I get a plus, OK? Or formally, I can add a plus, and then, I mean, yeah. So if I add this thing a plus, so that's why this condition holds true. OK, so we found equality, and the theorem is proved. Very good. OK. Yes, please. Sorry? No, only for, OK, for x0 it's 0, you agree? And it's 1 Lipschitz, you agree also? So it's finite everywhere in Rn. It's Arcella-Ascoli, I think, or something. If you have family of 1 Lipschitz functions, all of them are non-negative at 0, and the supremum is 1 Lipschitz. In fact, u of x is smaller than x. There's no question about finiteness of u. It's a bounded function. Not bounded, locally bounded. OK, now I want to proceed with the structure of the minimizer. OK, so we know that we can look at the optimum transport through gamma or through u. There is also an option to look at through T, through the optimal map. But this would not be helpful for us now. OK. By the way, just a remark is that about uniqueness, so gamma or T are in general non-unique. so are not uniquely determined. But the thing which is easy to work with is U. But at least, okay, U up to a constant. So let's say that grad U is uniquely determined, at least in the support, almost everywhere in the support of U. Okay. Okay, so we have this function U, and somehow, okay, and now I want to understand a bit more deeply how one of its functions look like. In particular, the one of its function U that occurs in this optimal transport. Okay, so what we understand from this proof is that it's very important to look on segments such that U of y minus U of x equals x minus y, the distance between them. Because if you have 2 points like that, that's the maximal speed. So U moves from x to y the maximal speed, because it's a one of its functions. It cannot go faster. This means that necessarily U grows with speed 1 along the interval, the segment xy. Right? I know that the value in the middle is the average of the values at x and the values at y, because it must go with maximal speed 1. And moreover, if U is differentiable, then it must point in the direction of this segment. Then it must point, it must be parallel to the segment. Or point in this direction, because you know the speed here is 1. So if there is some component here, it will contradict, it will violate the y-ellipticness. This is the maximal possible speed, speed 1, and it must be parallel to this segment. Okay, and these are called, okay, so I said transport rays, so transport rays of a one-Lipschitz function now, in general. These are line segments. So let me call, I think I want to open, yes. So these are maximal open segments, excluding the endpoints apparently, on which U grows with speed 1. And you see that it is called a ray, not a transport segment. So this means that this is maybe a ray or a line is also okay. Okay, so these are transport rays. And what we understand from Kantorovich duality So for Kantorovich duality, we understand that transport happens along transport rays. So the optimal transport, happens along the rays, along transport rays. It's mine? Okay, good. Right, so these transport rays. Let's look at some examples of these transport rays in some cases. And now we focus, we kind of almost forgot the fact right now that there is some measures that we transport. We only investigate a one-Lipschitz function U. We want to understand how its transport rays look like, okay? There are some Lipschitz functions for which there are no transport rays because, I don't know, there are constant functions like that. These are kind of not relevant for us. We care about strained Lipschitz functions that have many transport rays. So for example, let's look in 2 dimensions on the functions that on x1. So if this is a one-fifth function, and what are the transport rays? Supposing the unit square, the transport rays on which it goes with speed 1 are just parallel line segments parallel to the x-axis. Right? These are the transport rays. Right? They form a beautiful partition. And let me, for reason to be clear in a moment, let me try to explain to you what is the disintegration of pressure with respect to this partition. So what do I mean? I just mean the following thing, that since I have this partition, whenever I have some function Rn, I may integrate it first on these transport rays and then on the space of transport rays. So I have this, the Fubini's theorem. It's a big word for something very simple now. So I know that for any phi or whatever, some test function, the integral of phi on R2 is the same as integrating first kind of on x2, which is on the space of needles, on the space of transport rays, and then on each needle like that. Okay, that's an obvious thing. Too obvious that you don't see the point here, probably. The second example would be more meaningful, maybe. Let's look at the Euclidean distance. Okay, so u of x is the Euclidean distance of x from the origin, still in R2. Okay, so what are the transport rays here? Here it's natural to draw a circle, because u goes with speed 1 along radii. Radii says radii from the origin to infinity. These are transport rays. You can note that it's not a complete partition because, I mean, this point here, in my definition, does not belong to any of the transport rays because they are relatively open, or some definition it belongs. But anyway, you need to throw out a small point. It's only almost everywhere. These are transport rays. And now, the disintegration here corresponds to polar coordinates. So if you want to integrate your function, let me do it with complex notation. So if you want to integrate your function first on each needle, then you do it as follows. So you integrate it over from 0 to 2 pi, and then from 0 to infinity. So this is the space of needles, the angle, the theta. And here you have phi of r e to the I theta, dr. But that's not enough. In Fubini's theorem, there was no Jacobian because they were parallel, did not get closer or shorter or further from each other. But here you should have a factor of r. Okay, so this is a Jacobian factor, or we call it also the needle density. So it's important to recall that if you have a partition of Rn, the induced measure could have a density which reflects the fact whether the needles get closer or shorter to each other. In this case, the Jacobian is just r. It goes linearly on each needle. Okay, so if you want to integrate a function, you put some density, goes linearly on each needle, integrate the function on the needle, and then integrate over the space of all needles. And just note that in both cases, the needle density was log concave. Just some coincidence, or not a coincidence. Okay, but this is something we note. Very good. Okay, now let's discuss the situation in general after we saw these two. Any question about these examples? So what is the general situation? This integration of measure of conditional probabilities. Okay, so recall that we have these two measures, mu2 and mu1, and we have mu, which is the difference of 2 minus 1 minus the other, 2 minus 1, okay? So mu is a non-positive measure. I don't know, maybe here it's like positive and here it's like negative, so something like that. Okay, now we actually, okay, so as we said, I mean, later, I mean, transport rays form a partition of its support up to measure 0. of the support of mu up to measure 0. Okay. Now it will be convenient to fix some ambient measure lambda. So let's set f to be the density of mu with respect to lambda, where lambda is probably the Lehec measure. On Rn, or maybe some fixed, some reference low concave measure on Rn. That's also okay. Okay, maybe absolutely continuous. Measure on Rn whose support, okay, whose support is Rn. All of Rn. Okay, so this is the function f. Let me just to be sure that I'm not, so this is mu, the density of mu2 minus the density of mu1. Okay, now, so the assumption that mu1 and mu2 have the same total mass means that the integral of f is 0. Okay, so f is the density of, let me just recall that f is d mu to d lambda. Then the integral of f d lambda is 0. Okay, and now we can formulate the needle decomposition theorem. Yeah, so we formulated before the break. And then, so what's the needle decomposition theorem? So it goes back to the work of Evans and Gangbu in '98, and Caffarelli, Feldman, and Kannan. Or 1 or 2. And I did low concave part in 2014. Okay, so I mean, under the above assumptions, there exist certain objects. So first of all, a space of segments. So omega is a collection of disjoint segments that form, let me put a partition of all of Rn, but I allow singletons. And there is some measurability issue. I mean, there is something called measurable, it's a measurable partition. And segments could mean singletons also, or rays, or lines, any convex one-dimensional set thing, okay? And they are transport, at least those of positive lengths, are transport rays of U. Okay, and then there is a family of measures which corresponds to these measures in polar coordinates, the measure on each radius. So each radius has a measure with density R. So now we're going to have something slightly more complicated, I mean slightly more general, not complicated. So there's going to be some measure on each segment. I'm not saying that it's going to be the Lehec measure, like in the Fubini case, or with density R, but it's going to be, there is a family of, so a measure mu I for each segment I. So for each I, for each segment I in this collection, we have a measure mu I supported on I, on this segment. And we have a measure, I think it's called nu, on the space of segments. And there is some measurability issue which I don't state on what I call the space of segments omega. Such that we have a disintegration of measure. So the original measure lambda is the average or the integral of mu I. Okay, so the original measure is the integral of these measures. So this is called disintegration of measure or conditional probability. This means that for any test function, so this means that for any phi test function, smooth completely supported, the integral of phi d lambda would equal phi, say, in L1 of lambda. The integral of phi d lambda is the integral over of this. We have this Fubini type theorem. So this is what means that we have this measured decomposition. Okay, so it's a more general way of doing polar coordinates. We do integral on each needle with some density, and we have, and if I do the integral over the needles and then integrate over all needles, I reproduce the integral with respect to the original Lebesgue measure. Okay, so this is general. But we have two more properties. So two important properties. The first one is that each mu I is log concave on the interval I. Okay, and in fact, in the Lebesgue case, even more is true. In the Lebesgue case, it's going to have log concave with smooth density, even sin-infinity smooth density. In fact, it's a polynomial function in the Lebesgue case, polynomial of degree n-1. And second, such that, okay, almost each. Okay, for nu almost any I, for almost any I, mu I is log concave, and the integral of f with respect to mu I equals 0. Okay, this is called mass balance condition. Okay, so these are two important properties, low concavity on each needle, and the fact that the total, so remember that the integral of f d mu was equal to 0, but we retain this property separately on each needle. Okay, so after the break, we'll prove this theorem and see applications. So now 10 minutes break. We resume at 15.